All right, so these are the answers that I have. I'm going to show you the IV with a solid line and the DV with the dashed line. So number one, does listening to classical music improve children's reading abilities? The thing that you're manipulating is whether you're listening to classical music. So maybe you're choosing to listen to different types of music or music and no music, that kind of thing. That's the thing you manipulate. And the outcome is how a child was able to read. Number two, alcohol consumption impairs scores on memory tests. The independent variable is how much alcohol you're consuming, and your dependent outcome is what your score is on memory test. Number three, your coffee consumption is the thing you're changing and manipulating, and your alertness is the outcome of that. And lastly, how your office layout is designed is the thing you're manipulating, and employee satisfaction is what results. Okay, so let's kind of brainstorm together. How might we design an experiment to test our hypothesis? And what, in this case, in our an apple a day keeps the doctor away question that we have, what are the independent and dependent variables? So here we're looking at the thing that we can actually manipulate is the apple a day. So whatever we choose to define this as, we either, can have people eat an apple versus not eat an apple, or eat healthier versus not eat healthier, that kind of thing. And our dependent variable, the thing that we're measuring out of that, is the doctor part. So either, makes fewer visits to the doctor's office, or is overall more healthy. Whatever measure outcome we can do, there is our dependent variable. So let's kind of think about what this might look like. Here's a schematic that I've put together that might represent how we do this experiment. So starting on the left, first we're going to gather our sample. Remember, sample is the smaller version of the population. So for instance, maybe we have just purple people and pink people. We're then going to split them up. So we're going to have two different groups. We're going to have what we call an experimental group that gets the manipulation, the thing that we're studying. And then we have a control group that doesn't get the same, the thing we're studying. It's important that they get all additional things so that you keep as much constant as you can. The only difference between these two groups should be the independent variable that you're studying. So this group is going to serve as our comparison. That way we can isolate just the independent variable of interest and measure the outcome. So here's kind of the setup of how this works. And our experimental group is going to be given our apple a day. And then at the end of whatever period we're studying, we're going to measure how healthy they are, how many times they visit the doctor in both groups, and see if there's actually an effect. See if one group, visits the doctor more than the other. So say we did the study in this schematic. Say that the purple people in the experimental group had fewer doctor visits than the pink people in the control group. What would you be able to conclude? Could you say that, yep, it's the apple. The apple a day keeps the doctor away. What else do you think might have influenced the results potentially? Is there anything else you should have thought about, or things you might be skeptical about if I just convince you, if I try to tell you that this is the truth? So one thing to consider is that I've got entire groups made up of similar people. So there might be more to this story that we're not considering. What we call confounding variables, or variables that are irrelevant to the hypothesis we're testing, but secretly alter our conclusions. So they're kind of the behind the scenes sneaky kind of like extraneous variable that we need to try to minimize. So this might be things like any sort of individual differences you can think of, things like differences in age. So if you have a sample that's largely older than the other, maybe age and kind of growth in general is the factor that's actually contributing, or socioeconomic status, IQ, things like that. So we want to minimize these. In our example here, with watering plants, so we manipulated how much water these plants got, but maybe we didn't consider the weather when we were measuring our plant growth. Maybe certain plants grow better in different climates or in different seasons. So we can't necessarily draw broad conclusions if we didn't control for these external things, especially maybe if we planted these plants in different areas or got different types, species of plants. There are certain things that you need to control for that if you don't, might actually impact your results more than you want it to. So going back to our schematic, let's see if we can do this a little bit better. So to minimize confounding variables, the best thing we can do is use what we call a random representative sample. So it's random because we're taking people from a wide variety. We have red people, orange people, etc. And it's representative because it's more diverse. It's more likely to represent the general population than just perhaps using two groups, so, purple and pink. So that way, if perhaps being purple is impacting your health, for instance, maybe everyone in the purple group just happened to be smokers and the pink group weren't. So it's smoking that actually influenced your health, not an apple. We need to be able to distribute these individual differences across our two groups to kind of limit those confounding variables. So what we're going to do instead is randomly assign them into both groups. So they don't get to choose what group they're in. We don't get to be like, okay, all the warm colors in this group and the cooler colors in this group or anything like that. We just want to randomly, distribute those differences across so that if there are individual differences in IQ or socioeconomic status, they'll wash out because at least they're kind of present in both groups. One thing to note though, you can't always randomly assign your people. It sounds all great in theory, but for instance, if you're studying whether men or women are better at math, you can't assign someone randomly to be a man or a woman for your study. Or for instance, if you're studying the effect of a brain lesion on language processing compared to people who don't have brain lesions, you can't just assign someone to get a brain lesion. You see where I'm going. So not always ethically feasible, but if you can, definitely randomly assign your participants. And then the rest of the study can stay relatively the same. But now when we measure the dependent variable, we can be a little bit more confident that we've accounted for all these confounding kind of extraneous issues. And perhaps the results that we get are a little bit more pure and a little bit more representative of just the apple thing.